Hello again, folks, in MAT-113.
Today, as promised, I'm going to go over the solutions to the final exam.
Here's the calendar. Verify. Where's the date? Okay, today is Tuesday, May 11th. And my American Express bill is due today. I thankfully paid for that already. But the final exam you should have available as a PDF by now. I mailed it, I think, last Thursday. Now it looks like this. I think it's something like 13 pages, I forget offhand. Anyhow, I'm going to go through these. Anything that is pertinent should be written on it, adjacent, so you don't have to go looking for tables or anything like that. Okay, if you're going to follow along, do print that out. And I will fire up the projector here. It's a little slow today. It's all mine. Okay. Let's see. Adjust the lights too. And I think I'm gonna have to move my camera. Let me see. Ever so slightly. That's not so bad. I'm gonna try to project it, and then I'll just do the problem superimposed upon it. Cleaning agent there. What was I looking for? I may need another markup. Let's see. I don't think this is gonna be important, but keep some extra markers handy just in case. Okay. Yeah, that's too much. Okay. The first two, the first 20 of these are multiple choice because I swiped them from the test that I had given you. That was the first test. This is asking you to use inductive reasoning. If you're curious, just from the sake of distinction here, inductive versus deductive. Reasoning. Inductive is basically you start with specific examples with the intention of forming a general conclusion. Deductive, by contrast, is you start with basically a rule and you apply it to a specific example. And more or less opposites. Without belaboring it, let's just look at this. Here you see a pattern basically forming. So you have some specific examples here. All right. One thing that is consistently true is that there is a 6 in the front of each of these. So if you're going to expect a fourth term, it would have a 6 naturally. If you move over and then you see 1, 10, 100, those are powers of 10. So this would be 10 to the 0, 10 to the first, 10 to the second. In theory, the fourth one would be 10 to the third, which is the same as 1,000. Okay. Then adjacent to that, you see some consistency again. There is 2's. and then the factor that is next to that grouped together is 1, 2, 3, so assume that it would be 4 would be the next one. Right. Having seen those specific examples, we form the general conclusion that this is the pattern, basically. It would be 6 times 10 to a power, right, times 2 times n. So in theory, since this has to be 10 to the third, n minus 1, something like that. So when this is 4, that would be 3. And when this is 3, that would be 2. Okay. Anyhow, to actually determine what this would end up being, it's 6,000, right, for the first group, and then times 8, which would make it 48,000. And that gives you choice D here. This is the next one. This is a pattern drawing the next figure. All right. You see a circle, and then it is basically encapsulated by a square, and then the two of them are encapsulated together in a circle. So with this limited pattern, one might predict that the fourth term here, the fourth example, might look like this. All of that which had occurred already encapsulated by a square, and then the next one would be enclosed by a circle, and then enclosed by a larger square, and so forth. All right. Of the choices here, this would be D. Not too bad, right? These two problems are about estimating. Remember, when you're estimating, you're rounding first and then you're applying the operation. So, let me get the book out of the one here. The instruction I had given was, estimate by rounding to the nearest 100. Right? Know your place values, right? Especially the first few. Alright, if here's a decimal, alright, immediately to the right of it would be the ones place, and then the tens, and then the hundreds, and then the thousands. You really should know further than that, but if that on this side is the tenths place, THS, remember the suffixes are all to the right of the decimal point, and then the hundredths, and then the thousands, THS, and it goes on into infinity that way. Okay. So in this case, if you have they're all whole numbers really, so it would be practical to round to the hundredths place, which is the hundreds place rather. So here, aside from knowing the places, here's the strategy. Remember, if this is where you're rounding to, then where you end up having to look to decide how this rounds is immediately to the right of it, right? Which means that if this is 838, you're going to look at the 3 that is immediately adjacent to the 8. If that number, drawing an eyeball to simulate that place, all right, is 4 or greater, 5 or greater, and you round up. If that number that you're looking at is 4 or less, then you round down. Now what that amounts to is that when you're rounding up, you're going to change the digit of 8, in theory. When you're rounding down, then you're going to keep that digit, and then anything that is to the right of it, you're going to simply replace with zeros. So this ends up being 800 naturally. This over here, 566, alright, is 6 in that place. Alright, so this changes to 600. And then when you get to 967, alright, because you're at 9 in the place that you're rounding to, the hundreds place, you can't fit a 2-digit wide number in that space, so it ends up encroaching on the thousands. Alright, being that this is 6, alright, this ends up being 1,000. And then the next one, 800. And then this one, 500. Okay. So if it's just an adding, all right, add them as you would. All right, 1,400, 2,400, 3,200, 3,700. So you would end up having B. All right. The hard part for people usually when they're rounding is that they misconstrue the instruction of rounding up and rounding down. When you round up, you would change this digit to one number higher. Right? That's what happened in the case of this 566 here. It becomes 600 instead. But when you round down, all right, as in the case of this 838, you're not changing the 8 to a 7. You're changing the things that are beyond it to zeros. All right, so do be careful of that. All right. Anyhow, the answer should be 3,700, so B. This is a similar problem, except that it is now expanded just slightly. Subtraction. All right. I, again, gave you the suggestion of rounding to the 100 because it was practical in this case. The truth of the matter is, if you're asked to perform an estimate, there's a spectrum of answers. Some are probably more accurate, that is, they're closer to the exact answer, but less convenient, right? In this case, it seemed fair enough to go, you're gonna round to the hundreds place, right? So in the case of hundreds, tens, ones, remember that you are rounding to here. In order to decide how that actually works, you're going to look immediately to the right of it. So I'm putting an eyeball there. Okay? So based upon this 4 sitting here, alright, this 743 would round down. Alright? It follows this path of logic. Alright? The number that we're looking at is 4 or lower, so we're going to round the whole thing. The whole thing. Yeah. Which makes this 700. And then when you get to 272, based upon this being 7, this will be rounded up. Alright, so this would be 300. And actually 700 minus 300 is 400, so that would be choice C. When you get to 5, I gotta back off on this a little bit. You estimate the answer by rounding the first number to the nearest 100 and the second number to the nearest 1,000. Yeah. So, I'm trying to see. So the thousands would be next place over, thousands. When you're doing multiplication, you tend to, depending upon the breadth, that is the width, so to speak, of the factors, you might round to different places for convenience. Remember that the whole point of estimating is to make things easier. So it's arguably easier when you have a nice round number times a nice round number. All right, then you don't have to go through the intricate work of distributing every number to every other number when you multiply. Anyhow, the first number is three digit wide, so we're going to round to the nearest 100. And we're going to follow the same pattern for the logic from before. So this 231 would be reasonably to just 200. All right. At the same time, this 4854, we're going to round to the thousands place. So we're going to decide how to round based upon an 8 here. Right? Basically, we're shifting from looking here to looking here. All right, and then since this the number that we're looking at is 5 or greater, it would be 8 in this case. All right, we're going to round up. All right, so the whole thing is going to be rounded to about 5,000. Right. Now another shortcut is that once you have the factors, all right, in the rounded form that they ought to be, pay attention to the non-zeros, all right, and just multiply those two. So 2 times 5 by itself is 10 naturally, right? Then, to simplify your life, count the number of zeros that are in each of these factors. So there's 2 here and there's 3 here, which means that after your 10, and I purposely put this in blue, include another 5 zeros. And this is what you would have. So you have 1 million. So B. Okay. Division, it gets out of the 4 operations, adding, subtracting, multiplying, and dividing is usually the thing that gets taught last of those 4. Because it really requires the prior skills. Right. It may sound silly, right? But when you divide, especially if you're doing long division, you need to have a frame of reference, and the frame of reference is multiplication, right? Because division is the opposite of that. Anyhow, estimating is for convenience. So you have increasingly more and more leeway as to how you round. In some cases, I've seen people round not so strict in terms of these 2 principles, but just to get something to work. That is to make the dividend and the divisor divide nicely, right? You can do that, right? If it's an estimate, it doesn't have to be the exact answer. It's about convenience. But we're going to try to stick to this as rigidly as we can, all right? So in this case, my suggestion was estimate the answer by rounding the first, the longer here, the dividend, to the nearest 10,000, all right? So here you go again. You have another space that you're going to hang on to over here, right? 10,000s. Thousands. Right. And this is the hundreds. Yeah. So you're shifting your focus once again. Alright, in this case to round to the nearest 10,000 for 43,000 means you're going to be looking at the 3. And I'm sorry it's so far away. Alright. Rounding to here, you're looking here to decide how you round. Alright, being that it's a 3, conforms more to this logic, which is that it's 4 or less. So therefore, we're going to round this to simply 40,000. Right. As for the other term, the other, this is the divisor here, the other part. We're going to round this to the nearest 100. Notice it's much shorter anyway, so it makes sense to round it to where the 3 is. And we're going to look at the 10s again. All right. So based upon 6, we're going to conform to this logic. All right. It's 5 or greater, so we're going to round up. That would make this about 400. Okay. Now, in my opinion, you're aware, of course, that there's different styles of dividing. We use the cone with the line through it. We have that sort of division box that is sometimes oriented this way, and elsewhere oriented like that. There's a forward slash, or there's just the line separating the top and the bottom, a fraction-esque ratio style of writing. When it comes to this stuff, estimating, I have found that if you're going to choose a style of division, how to write something, the fraction style would be the most appropriate, because then you could apply a very neat shortcut. All right? That is to take the first number and to put it above the line, and then take the second number and put it below the line. All right? Without involving a calculator, you can get to the answer pretty quickly. All right? If it were a fraction, you know how oftentimes you're asked to simplify a fraction, right? In that case, you would ideally look for the greatest common factor. Without delving into too deep, you could basically simplify it lickety-split. Cross out pairs of zeros. You can't get away with doing that with any other numbers, but when you have zeros here and zeros here in pairs, you can cross them out. The logic is, without thinking about it, that you're dividing by 100 here and dividing by 100 here. So it's all well and good because it's consistent, right? Then it's a matter of dividing 400 by 4, right? Which is just 100, right? Because 4 divided by 4 is 1, and then it has 2 zeros. So you have this choice D. Okay. I think I still need coffee. There's some water here. You're going, when you're doing with the word problem, as you see in example 7, we're going to get an exact answer, so we're not going to round in this case. In some cases, like if they ask you to round rather than simply, instead of using the word estimate, estimating implies that you're doing your rounding first, right? And then you're performing the operation. Rounding is 9 times out of 10, you've done the operation already, and then you round as an afterthought. All right, so do make that distinction. If you see the word estimate, you have to round first, not last. Okay. Now in this case, in a shop that sells a variety of nuts, the prices of some items are as given below. If Sarah buys 2 pounds of cashews, 1 pound of walnuts, and 2 pounds of raisins, how much did she have to pay for the mix in general? All right. Well, what I would do is, I purposely left some space here. All right. Just put the number of pounds next to the type of nut. So in this case, you see 2 pounds of cashew nuts. So next to cashews here, I will put times 2. And then 1 pound of walnuts, just times 1. And then 2 pounds of raisins, it's also 2. Right. And then you would basically compile these. Right? If it's just 1 pound, then it's $3.99 exactly as you see it. Now, as I'm fond of making this speech, I think I will once again. All right. If you're in the position of teacher, especially kids who are in elementary school or middle school, do them the favor, do yourself a favor too. Give them graph paper, because even if it seems really cuckoo to have to anal retentively put numbers in little boxes, if you teach a kid to do that, they'll be less likely to make a mistake. Alright? So again, it might seem a little, very super anal retentive to do that, right? But if you teach the kid, give them a little scaffolding. It's sort of like the bumpers at the bowling alley, it'll guide them in the right direction. Okay, it's not a bad thing. If you were to take a chemistry class, at least historically, they would give you a manual that is, lab manual that is a notebook that is graph paper. Why? Because you used to have to do things by hand, right? And you still should to a degree. Anyhow, I use the line as the place for the decimal, but the digits go around it like so. So since we have 1 pound of walnuts, it's 3.90 like so. This one is times 2, all right? We would have to figure out what it is first. All right, so if it's $4.99 times 2, I need the space. So I'm gonna put that up here, times 2. 0, 18, 980. So when you add, in this case you would have to add, they don't really specify that, I know, but it's only reasonable to assume that your bill is going to get larger, not smaller, all right? So you're going to add, not subtract, right? And we've already multiplied here. Anyhow, this is 9.80. One must, when you're adding decimals especially, right, be mindful of the decimal places. So they must all line up. That is the purpose of the scaffolding, so to speak. All right, now you have raisins as well, 310. So figure out what that would end up being. 0 to 620. Right? And then you would have that. Now if you'd like, you can put a plus sign here, you can put the equals here. All right. They're all collimated when you add or subtract decimals. Yeah, so you're going to combine everything in this far right here, which is 0 naturally. All right. You could do this since you're adding strictly in any particular order. All right. It occurs to me that 8 and 2 is 10, so that might be a little bit easier. And then plus 9 is 19. So I'm going to put a 9 here and then carry the 1. And then similarly, you're just adding, so it's commutative. You can do it in any order. 1 and 9 is 10 again. All right. 13 and then another 6 is 19. So 2 digits, 1990. Good year, right? So C. Okay. Let's see. Next one, an electric pole 16 feet high casts a shadow that is 8.5 feet long. What is the length of the shadow of a 21-foot pole? Round the answer, notice that they don't say estimate, round the answer to the nearest whole number. That is round after, not for the calculation. Again, if instead of round they said estimate, you would have rounded first, right? And in this case, you're rounding after the fact because the word estimate is not here, all right? Estimating is rounding first. All right? Just rounding is rounding last. This is one of those types of problems that I would encourage you to draw a simple picture. All right, it summarizes a lot, right? A pole. What is an electric pole? To me, it should just say a telephone pole. So you have a pole of some sort. All right, and it's planted in the ground. All right, and here's the sun over here. All right, so it's casting shadows. The pole itself is 16 feet tall. And it casts a shadow that is a little more than half of that. So the shadow length is 8.5. Right? And from that information, assuming we're talking about the same time of day here, if we had a pole that was just a little bit taller, 21 feet, we can estimate what the shadow length would be in that case. All right. This would help you write what is referred to as a proportion equation. Right? And a proportion equation is firstly an equation, so there's equals in it. And it takes advantage of the relationship between similar figures. Now you see something that kind of looks like a triangle here. This is supposed to be a shadow, I swear. If two figures are proportionate, they're similar, right? That means that they are, although not the same size, right? The relationship of these dimensions are such that they are corresponding, right? They might be larger or smaller by some consistent factor. So what we can do is write a ratio that is set equal to a second ratio, right? Just be consistent. I would say if we're talking about two things, measurements, height and shadow length, all right, let's just make, for the sake of consistency, the height the top dimension and the shadow length the bottom dimension, okay? There's probably more than one way to arrange the numbers that you see here into these four places, all right? But the safe bet is to be consistent. So we'll make this the first pole, and we'll make these dimensions from the second pole. All right, and the tops will be the heights. So if you see 16, we're going to put a 16 here. All right. If you see 20, we'll put a 20 in this void. All right. Now this is known that the shadow length is 8.5, so I would put 8.5 here. And in this case, we're looking for the shadow length of a 21-foot pole to answer the question. So use a variable. You can leave a question mark if you like, but I would use a variable. So a logical one might be S for shadow. All right. And now you have something that you could solve, a proportion equation, which you solve via cross multiplying. Okay. What does that entail doing? Well, you multiply diagonally this way, right? And you could write those adjacent to each other. So say it's 16 times S. I'm going to use a dot for multiplication. If you want, you could just kind of squash them together further still. All right. I'm going to resist doing that for a moment. Right? And then you multiply diagonally this way. So it'd be 8.5 times 20. 8.5 times 20. Now, if you want, being that you have regular ordinary numbers here, 8.5 and 20, you could use your calculator, do it by hand, and simplify that down to one thing. All right. I was encouraged, and this is a good habit, to resist that until you have all of the numbers exclusively on one side. There's a lot of things that you can do basically without a calculator. Not that it's a sin to use that. All right, if you're strategic. So if we were going to solve a problem like this, we would have to do so algebraically. When you solve algebraically, you perform opposite operations to move things around. So if you want to move something over equals, you perform the opposite operation. What is the opposite of multiplying by 16? Dividing by 16, and the tendency in algebra is to use this symbol for division. And if you do it here, the Zen balancing act, the beauty of algebra is that you do it consistently, so you do it here as well. Right? The effect, strategically so, is that these will cancel and just be one. Right? And that leaves you with the thing that you're actually looking for, which is the S variable. S would be equal to the outcome. Now, since I've strategically arranged all of the actual numbers on one side, you can, if you want to, right, type this into your calculator at will in this order. Everything on the top, 8.5 times 20, division symbol, and then 16, and it will probably spit out an answer and won't give you any trouble. If you don't have a calculator, or you want to make it a little bit easier when you're entering stuff, now that everything is where it's supposed to be, you can simplify this. This is in what you might call factored form. And when something is in factored form, you could sort of blend together the parts from the bottom with the parts from the top. Right? You might recognize, if you have some information internalized, namely in multiplication tables, you could simplify this a little bit. All right? It's not going to be perfect, but it's a good strategy to check anyhow. 16 and 20 are both made of the number 4. Therefore, you could simplify each of those factors by 4. Means that this would be 4 down here, and this would be 5. Okay. And then you would have slightly smaller numbers to deal with. All right. Regardless, if you multiply any of this stuff together, let's see what you get. All right. You should. Oh, sorry, that's 21. 21, ding dong. So, okay. Well, thank God I checked, because since this is in fact 21 instead of 20, I can't simplify that. So I'm stuck with it. All right. Just go ahead in that case. Brute force multiply. All right. And then divide by 16. All right. In which case you will get something like 11.1565, I believe. Right. And if you are instructed to round to the nearest whole number, that's the ones place, this is approximately squiggle equals 11. right? The unit was consistently feet, so one could anticipate that this would be feet. The shadow length here would be 11 feet. There's another way of referring to this. They call it shadow reckoning. It's a strategy by writing a proportion equation of measuring things indirectly. Right? Now, arguably, it would be easier to measure along the length of the ground, right, where a shadow would be, right, rather than measuring things that are much taller than you. Right? So you can do it indirectly via proportions if you like. Anyhow, you should get 11, which would be choice D in this case. Moving on. Right. Each gallon of porch and deck paint covers 150 square feet. I should erase the gobbledygook first, sorry. Each gallon of porch and deck paint covers 150 square feet. How many gallons are needed to cover 1,500 square feet? If you could do this intuitively, that's a blessing, and I would never resist that. But being that I teach MAT-114 in addition to MAT-113, right? The strategy of taking what is given and then multiplying by a conversion factor would be a good subject to broach, right? If I haven't already, and I believe I did. Basically, you can get what you want out of an equation that you write yourself, right? By taking what is given and multiplying it by an appropriate conversion factor. The conversion factor is essentially a fraction that you could rearrange as something over something or switch it, right, at will. Right? In this case, there's a hidden conversion factor. This would be useful in a chemistry class. Because some of this is more verbal than it is symbolic. For example, each gallon is a way of saying 1 gallon. Right? Porch and Deck is the name of the brand, apparently. And then it tells you that 1 gallon covers, so that's say, for all intents and purposes, equal 150 square feet. Right? This, which is essentially written out horizontally, 1 gallon is 150 feet squared, is another abbreviation for square feet. If it covers, then it is that, essentially. You could write this in the style of a ratio. It is a glorified fraction, if you will. So you could put the 1 gallon on the top, you could put the 150 on the bottom if you like. I'll do that here. 1 GAL for the abbreviation, 150 for the feet squared here. Or, if you like, 150 over 1 gallon. Right? Depending upon what's given to you and what you actually want in the model here, we're going to choose how we orient this conversion factor here. Right? Now the next part of it, and what is actually the question, is how many gallons, so gallons is what you want, is needed to cover 1,500 square feet. This is the given term. So up here, where I have the word given, right, I'm going to basically substitute 1,500, and I'll erase some of the gobbledygook just not to get distracting here. Okay. In place of given, I'm going to substitute this value. 1,500 sits in this position, right, and it's feet squared. 1,500 feet squared. Times equals. What I want is number of gallons, so maybe I'll just substitute in question mark, since it's unknown at this point, gallons, here. All right. And now the middle term here, namely the fraction, right, is either going to be oriented like this from the information. Oh, that's not too faint. 1 gallon over 150, or 150 over 1, right? Depending upon what I have and what I want and how I want it to cancel. Right? That's the whole strategy for this. If feet squared is not the thing that you want, then feet squared has to be canceled, which means that feet squared would be the bottom here in the conversion factor. Right? If gallons is what you want, then gallons has to be on top. So gallons would be here. If you take the time to decide where the units would go, that will help you decide where the numbers go, because the numbers are ever attached to those units. All right? The relationship is 1 gallon is 150. So 1 would have to be here, and 150 would have to be here. Now, although this might seem a little arduous, once you get good at it, you do it a lot faster than you see me doing it, right? I have to take my time, as I'd be remiss if I didn't. Anyhow, the beauty of taking the time to do this is that you get the satisfaction of crossing out stuff, right? And it helps validate your suspicion about how the answer should be done. It should be completed. This unit is down here below the line, and this is technically above the line. You can put a 1 here if it makes you more comfortable. So the units of feet squared are canceled, right? Words are canceled that way. Abbreviations for words are canceled that way. Numbers would cancel that way, right? Now, if you want, you could also simplify 150 and 1500 because they are related. Or do it brute force. What you are left with essentially is 1500 times 1, which means that there's a 1500 above the line, and then there's a 1 times 150, which means there's 150 below the line. And you could, if you want to, pull some tricks again. If you see a pair of zeros, you can get rid of 1 pair, and then it's 150 divided by 15, which is not too hard. Because if it was just 15 into 15, that's 1, and if it has a 0, it's just an extra 0. So the answer is 10 gallons, which is A in this case. When you get into Chapter 7, which is section, this is for the class MAT-113 instead, you do this a lot. If you were to take a chemistry class, you do this a lot. They call it stoichiometry, right? And do unit conversions all the time in science class. Anyhow, this is a very basic thing. The hard part, I would say, is translating it from something that is English, which is somewhat confusing, right, into something that's more mathematic, more symbolic. Confidence helps. And you get confidence by doing something a lot, believe me. I think I need a cup of coffee because I'm still stupid. Very tired. Forgive me. I'll be right back. I'm in my kitchen. So I'm just going to pour myself the remainder of my coffee from my pot. Maybe I should zoom in on this a little bit. Okay. Missy and Carl work at different jobs. Right? Missy earns $6 per hour, and Carl earns $5 per hour. This is the downside to zooming in. Yeah. I think that's a little bit better. They each earn the same amount of money, right, per week. Right? But Carl works 2 hours more. How many hours a week does Carl work? This is one of those types of problems that you may have to go down sort of an indirect path, all right, to get to the answer eventually. This is nonetheless a good exercise, all right, in translating things from English into something that is more universally understood, a mathematical equation. When you see things like this, per, all right, the word per implies a rate, all right, and a rate is a glorified fraction. It's something above something else. All right, so if you see Missy earns $6 per hour, then this is your first, it's a quick conversion factor basically. It's exchanging money for time. You'd have this, and this pertains to this person, Missy. All right. Simultaneously, this other person, Carl, all right, earns $5 per hour. So his rate would be 5 over 1 hour. All right, and that's Carl. All right. Now, interestingly, they each earn the same amount of money, all right, per week, but Carl ends up having to work longer, all right, in order to accomplish that because he gets paid less. Right? Let's take advantage of some information that's not explicitly stated, but still implied, all right? They each earn the same amount. Same means that something is equal to something else. All right, so we could set up the scaffolding for a very simple equation immediately. Sameness implies equality, right, without explicitly saying the word equals. So just put a question mark and then the equal sign and then a second question mark. Never feel bad when you're trying to construct an equation. If you start out more verbal, you can slowly whittle it down to the essential eventually. Let's say that we put things pertaining to Missy on one side and things pertaining to Carl on the opposite side. So what we have already is basically this. The information about Missy is that she gets paid $6 per hour. So over here, I'm going to put $6 per 1 hour times so many hours. Right? Would be how much that this person, Missy, gets paid, all right, in a week. All right. On the opposite side, I would start out, and I may have to modify this, but I'm going to put Carl's rate of pay, which is $5 per 1 hour, which one would have to assume that he would be paid some amount of hours right over here. You know what? Not to confuse you, let me just put a question mark here, all right, for a moment, because the number of hours, and this is where it gets tricky, would have to be substituted by not a number, but an expression. Right? In order for this relationship to be true, maybe I should just use the question mark here for a moment as well. Right? See what I mean? If you start out, sort of debating in your head, even if it's in front of an audience, don't feel bad. All right, you will make it. You'll be a success eventually. You just have to have patience, stick-to-itiveness. All right. Anyhow. What I'm going to substitute in place of question mark is probably the letter M, because the letter M could represent basically Missy's number of hours. We'll call it M. All right. Carl is expressed in reference to her. All right. Let's use K for Carl. All right. As in Carl hours, because there's a comparative phrase here. It says 2 more hours. 2 more than whom? Or 2 more than who? See, English was never my strong suit. 2 more than Missy. So I could kind of craft an expression that explains Carl in reference to her. All right. So if Missy is M, Carl is Missy plus 2. That's what I'm going to sneak in here in place of this question mark. We agree that if it was 1 hour, it would be 1 times 5, right? And if it was 2 hours, it would be 2 times 5, right? Or 2 times 6, or what have you. In this case, because of this comparative phrasing, all right, I can't just put a number here. I'm going to instead put an expression. Right? So that's going to go here. Right? To write it a little bit neater, a little bit cleaner, I'll put it over here just because I have some space. Right? It's going to be $6 times Missy's number of hours. The one down here in the unit is really not imperative. Right? So I'm just going to reduce it to its most simple elegance here, which is 6 times m. All right? And on the opposite side, I'm going to put Carl's reference, which is 5 times this quantity, which I will have to group. All right, Missy plus 2. All right. What is going to happen is that we have an equation that is going to first indirectly solve for Missy's hours. All right, which we will then use to answer the question of Carl hours. This is why I say that it is indirect. All right? There might be another way to do this, but this is the way it occurred to me, right? Based upon the phrasing of the question here. All right, so we're going to go indirectly to solve for Hall first. Notice that there's just m's here for Missy, and then from that information we'll substitute it in here, the second equation, technically. All right, I'm just using that much of it, the expression, to substitute here. Okay. So, let's do what we can, all right? On this side, we can't really simplify much more than getting rid of the dollar signs, perhaps. All right, so it's just 6m. On this side, we have 5 times that expression, m plus 2. So what I can do is, I can get rid of this parentheses that I was obligated to put here by distributing the 5 to each of the inside contents here, all right? The abbreviation for 5 times m is just 5m. The outcome of 5 times 2 is just 10, which means, for the sake of space, what I end up with now is, I'll get out of the way in a second, I swear, 6m on one side and 5m plus 10 on the other. Okay? Now, in order to solve for m, I got to get the m's exclusively on one side, so I'm going to have to fall back on algebra again. Remember, when you solve something algebraically, you perform opposite operations to move things around. If I want to move something from here to here, then I have to perform opposite operations. In this case, that means either adding or subtracting. You're going to take not just the number 5, you're going to take the whole term. Right? It is understood that this is a positive if it's not written. So to justify moving it from here to here, I would have to perform the opposite operation since I'm going over the equation here. So I'm going to subtract 5m. You might get a little worried and go, well, I don't know what m is. How can I do that? It doesn't matter, all right? Because by sheer logic alone, something minus itself, all right, is going to cancel out of existence, all right, even if it's mysterious. And then I put it over here as well. That is the Zen balancing act. That is the blessing of algebra, all right? This is 6 minus 5, essentially. They're like terms. That leaves you with just 1m, which you could just reduce to the letter m. Okay? 1 is superfluous. It is an option that you don't have to take advantage of if you don't want to. All right? We're solving for Missy in this case. What's left over here? 10. And since m represents Missy's hours, that means that Missy worked 10 hours. We're now going to substitute that in this expression here to solve for how many hours for Carl, because that's what the question actually was asking. What's 10 plus 2? 12 hours. This person has to work 12 hours to accomplish the same amount of money, essentially. All right? Which is choice A. Okay? Here's more translation. This is a little bit more straightforward. What you see here. Okay. You may remember in the earlier part of the semester we compiled a table of suspect phrases, words that translate from English to something mathematical. Look for the word is. Right? The word is the equal sign. which means that everything that is on the left side of that is 1/2 of the equation, and everything that is on the right side of the is the opposite right side of the equation. Right? Now there are some things like the word twice, all right, which imply both a number and an operation simultaneously. Right? Twice means times 2, essentially. And if we're talking about a number, and this has to be an algebraic equation, you might use a logical abbreviation for that. So it's nothing wrong with using any particular letter, but since it's number, then I would say n. Right? You could say 2 times n, or you could be a little bit more concise and just simply press them together, which means that on this side you might simply have 2n. Now on the opposite side you have this expression, 10 less than. When you get to words like less or more, they are, beware, counterintuitive. Alright. You might say, alright, well less implies subtracting, and that is true, and more implies addition, and that is true. But because of the way that they're phrased in English, they're counterintuitive in where you actually write things. How you write. How you arrange. Right? Comparative words are like that. So even though intuitively you might go, all right, well, if this means minus, then it's 10 minus, resist the temptation to do that. Right? When you have comparative words, right, you're going to put, instead of 10 minus, what you end up having to do is write minus 10. It goes to the back. Right? That's why I say it's counterintuitive, because it shows up in your face first. But ironically, you're going to put it at the back, and then there's this gap in between. Right? What goes there is somewhat ironically the stuff that follows. Right? 3 times a number would just be the same as writing 3n. Right? And this, what you see here, is a satisfying equation. Right? In the choices that you see here, they didn't use n's, they used x's, but just look for what matches. Right? The thing that most closely resembles it would be this one. Right? 2x is equal to 3x minus 10. Right? Be careful. Less or more are counterintuitive, and when it comes to less especially, you really have no choice. You have to put it at the end. Okay. Let's see. Now when you get to this part, this is in reference to section 6.4. Okay. You have a couple of different models that would be good to know. You have things that vary directly. You have direct, inverse, joint, and combined models. Since they're models, we use generally, we're going to use y and x a lot. Right. The direct model of an equation is y equals k times x, say. And I will just put this this k in different colors to sort of emphasize its distinction from the other two. Right. If you have an inverse relationship between these variables, then what you would see is that one of them would be essentially a denominator, instead of on the same tier. I moved my curtain, sorry. Alright, when you have a joint relationship, then you have the third variable. So you might see something like this. Y is equal to, let's see how short it was, k, and then there's a third letter here, which we'll just call z. So all things multiplied, and a combination would be something like this. y is equal to x k z and a fourth variable w, something like that. Okay. There's a funny way to read these, all right? But let me read the question first. If m varies directly as p, right, that's referring to this model. It's just using different variables, right? If m varies directly as p, and m is 27 when p is 9, find m when p is 5. Don't be intimidated at all, all right? Just know that you have these choices to choose from, 1 of 4, all right? And if they say the phrase directly, they're referring to this one, all right? How, the awkward way that you would read this, y equals k times x, is y varies directly as x, okay? So what they've done in this case is what? They have switched out y with the letter m. Okay, so what that means is if n varies directly as p, in place of y, because it's the thing that is referred to first, we're going to use the letter m. So an m would go here. Right? As p instead of as x means that there's a p here instead of there. All right, instead of x. All right. So we have this. M is equal to k and p. Right? We've just changed basically the labels in the direct model. What we can do now is figure out what k is, because if there's 3 parts and it's just multiplication here, and they're telling us what 27, what m is and what 9 is, we can infer what k is. Right? So in place of m, I'm going to put 27. And in place of p, I'm going to put 9. If I'm going to solve for k in this instance now, all right, I just have to apply opposite operations. So if it's being multiplied according to the direct model, I'm going to divide by 9 here and here. And this is going to tell me that k is whatever 27 divided by 9 is, which should be what? 3. Right? Now, if I go back to that same model, m is equal to k times p, I could substitute in whatever values I need. Right? They ask us to find m in this case when p is 5. So we just figured out what k was without really being explicitly asked. Right? It's implied, and that's a 3 there. Right? And they're telling us that p is 5. So if the relationship going on here is that these two things are being multiplied, what's 3 times 5? 15. M is equal to 15 then. Okay? Just be aware of these choices and the awkward phrasing of them, right? Y varies directly as p. If you got to this one, it would be y varies inversely as x. You know? Okay, now the percentages here. Wheel 4 feet, please. Right is a percentage. Now be mindful. Remember, we have, that's not going to show up. We have percents, we have fractions, and we have decimals. And they're basically 3 styles of the same quantity, or they can be. Right, so one could convert a percentage to a decimal or a fraction. One could convert a decimal to a fraction or vice versa. One could go indirectly. Right? There's a lot of different ways to do this. Right? In general, when you're converting to a percentage, 2%, you're multiplying by 100. Right? From percent, you're dividing by 100. Right? That would be important in this case. If you're going to write this as a percentage, you're going to a percent, right? Which means that you're going to multiply by 100. and you're just going to tack on a percent symbol as an afterthought. The effect of that without involving your calculator is that it's just going to scoot your decimal place over twice, right, to the right. Right? So move twice to the right. Right? And if you're dividing, you're going twice to the left. Right? Do you know the difference? Right is that way, left is this way. All right, so this ends up making this 87.3%. All right, which is choice A. Okay, 5/8. You have it's written with the forward slash, right? This is a fraction. So the process, if you're going to a percentage, is still to multiply by 100, and then to attach a percent symbol. In this case, what you might do is write it out in the more traditional way, so that you have a top and a bottom and a top and a bottom consistently. All right. And then you can attempt to simplify first. I would encourage you to do that, but even if you did top times top and bottom times bottom, and you got 500 over 800, pardon me, 500 over 8, this is now in the style of a percent because of the multiplication. You would just have to reduce this to a decimal, apparently, because those are your choices, if that's the way it works out. Now, to make it easier on myself, I'm going to try to simplify a little bit. These are both even, so that means I can simplify by 2, but a better choice would actually be 4. All right, 8 divided by 4 would be 2 here, and 100 divided by 4 would be 25, which means that this would be 5 times 25 instead, which is 125. And then 2 times 1 would be 2. And then essentially half of 125 would be what? 62.5. 2 goes into this 6 times. 2 goes into 5 twice, which is 4. And the difference is 1, and 2 goes into 10 5 times. So it's 62.5%. Which is, again, coincidentally choice A. Okay. Now we're going to start with percentages. Okay, so when you're going from a percentage to whatever you need to, in this case, it is asking us to write as a decimal purely. All right, we are going to, from a percent, divide by 100. Right? So to divide this by 100, right, the effect is that it's going to move our decimal point twice to the left. So even though there's no decimal here, at least evidently, it would technically be after the 6, which means that the decimal point would now go that way, and you'd end up with 0.76. You can put a 0 here if you like for stylistic purposes. All right, but that would be choice C. Okay. This one is a little bit more tricky because it's simultaneously a percent and a fraction, but still bear in mind, you're converting from a percentage. So what you're going to do is, nonetheless, you're going to divide by 100. Right. If you write it out, what you would have in a situation like this, a little bit more traditionally, would be 3 sitting on top of 8, divided by 100 adjacent. And what you have to remember is that when you divide by 100, a fraction involving here, you would apply this technique: keep, change, flip. Right? You keep the fraction here as you see it. You change the operation, somewhat ironically, to multiplication. And then you compensate by flipping this to a reciprocal, which in this case, since it's 100, would be 100 over 1. Flipped is 1 over 100. Right. And because you've gone through the motions of dividing by 100 to begin with, this is no longer a percentage. Right? It's going to be purely a decimal. What you have here then is 3 times 1, which is 3, and 8 times 100, which is 800. And then you could attempt to simplify that. All right. If you were to do it brute force, I always drew the little division box here. Plop the top thing in here, and throw in some zeros to get rolling here. And you can go through the process. Let's see. An easier way to do it up front would be to convert this to a decimal first, and then make this into a decimal just by itself, and then apply the trick of moving the decimal point. All right, because it's easier to change that than it is to do this. All right, it's not impossible, but because of the nature of this, 800 into 3, not going to fit. 800 into 30, not going to fit. 800 into 300, not going to fit. But 800 into 3,000, yes, it will work. All right, it would be 3, which would be 2,400, and the difference would be 600. And then you have it's cumbersome, but it's not impossible. 800 into 600, the relationship of 8 into 60 is 7, which would be 5,600 in this magnitude here. And the difference would be 400. And you bring down another 0, and this one becomes unnecessary. 800 into 400 would be 5. And that would terminate at that point. And you would have it as it should be, all well and done. 0.00375. Hypothetically, if you would have taken 3/8 to begin with and converted 3/8 into a decimal first, might have been a little bit easier. 8 goes into 3, no, it's too small. But 8 goes into 30 3 times, which is 24, and the difference is 6. Notice it's the same relationship. 7 is 56, difference is 4. Alright, and 8 goes into that. You'd have 0.375. Then divided by 100 has the effect of moving this decimal point twice that way, and you end up with the same answer either way. Okay, so that is choice A again. Okay, on a biology test, the student got 19 questions correct but did not pass. On a second attempt, the student got 29 questions correct. What was the percent increase? And then round to the nearest whole percent, which is the ones place essentially. This is a formula, all right, known as percent change, generalized, and it could be an increase or it could be a decrease, depending upon whether you get a positive outcome or a negative outcome. It's a percent decrease when you have a negative outcome. It's a percent increase when you have a positive. The formula would look something like this. The new amount minus the old amount over the old times 100. That's the most concise way to write it. A little bit less elegant than I'd like. You could say original or initial, and you could say final instead of new if you like, but this is essentially it. The original thing and the new thing. Right? So, taking these numbers in, 19 was the original amount, so you would put 19 here and here respectively, and 29 would go here. The difference, which you must do first, and that's why there's this parentheses incidentally to focus here. The difference of 29 and 9 is 10 over 29 times 100 then, over 1. Right? There's no simplifying this up front, so you end up with top times top and bottom times bottom, which is essentially 1,000 divided by 29. That is a percentage. Now if you take your calculator and you enter 1,000 divided by 29, you'd see something like this. There's the decimal, 34.48 looks like. Oh, sorry, 19. Thing down here. 19, so this is the 19 at the bottom. So 1,000 divided by 19 instead, sorry. 52.6 something. If this is 52.63, whatever it is, percent, you're rounding to the nearest whole percent, that is an afterthought. We're going to round here based upon this. Alright, since this is greater than, this is 5 or greater, it's namely 6, we're going to increase that to 53%. So it's a positive the way it worked out, so it would be an increase. Right. Which is kind of obvious anyway because it went from 19 to 29. Okay. Now what happens below here is you have some percent equations. They're collectively referred to as percent equations, but you might, in some instances, actually be looking for the percent, and in others not. You're looking for the parts related to it. Okay. This is a good exercise in translating some things verbal. If you're, again, in a position of teacher, start with this. When you're teaching little kids, all right, how to decipher English and translate it into math, all right, this is consistently true, all right? The word is equals, all right? And the word of, as long as it's just of by itself, is times. So that means that if you have 150% of 390, that means that it's 150% times 390. The only thing that you would have to do is translate this percentage into something that is usable, which is either a decimal or a fraction. It's probably easy in this particular example to go as a decimal. So that would be 1.50 times 390. All right, and what do you get? You should get 585, which is A. Now in this problem, what percent of 115 is 1172? 11 and 72 hundredths, right? Is equals, of is times. You may not end up doing multiplication in this case because of algebra, but I would still set it up this way, right? The number that is supposed to be there is right where it's supposed to be. 115 is in between here. What's a logical letter for percentage? P. So if it's P times 115 is equal to 1172, sounds like an address. It's the Lavaro House, I believe. Is it? No, that's across the street. One of my addresses was 1175 once. Now you're going to solve this algebraically. How come? Because you don't have a letter time. You don't have a number times a number. You have a letter times a number. So, how am I going to justify solving for p, the percentage? I'm going to move 115 to this side. All right. I do so by opposite operations. The opposite of multiplying is dividing. And if I do it here, I'm obligated to do it here. Something divided by itself cancels, it's essentially into 1, so it's become a dud. What you're left with is the thing you're trying to solve for, p, the percentage. And then you would enter this into your calculator. All right. What you're going to end up with is that this is going to be a decimal, right? And you want it to be in the style of a percentage. So as an afterthought, you're going to take that decimal and you're going to multiply by 100 to make it a percent. All right. What do you end up with in that case? It's 10.2. Right? So that's it. Just to verify here. Let's see. 1172 divided by 115. Here you get 10.1019 is the decimal. That's a decimal purely, right? Again, if we want to convert it to a percentage to answer the question, it's an added step of multiplying by 100. We're changing the style, basically, of the answer, right? So if you have 0.1019, whatever it is, and then you multiply by 100, the effect is that the decimal place moves twice. And you have approximately 10.2, rounded, to the nearest tenth of a percent. All right, last of this bunch. Is the following. Okay, a store manager paid $110 for an item and then set a selling price of $150. Right? What was the percent markup? Percent markup, that is exactly the percent of change, but just giving it a name. New minus old over old times 100. Okay. Markup in general is the dollar value that is tacked on to the cost of an item so that a store turns a profit. Because if they just, as a middleman, if they just basically charged you what they paid for it, then they would go out of business. So they always tack on a little bit extra. And if they're really greedy, they tack on a lot. Anyhow, the store manager paid 110, so that's the original amount of something. And then the selling price is 150. So in the formula, that is percent change or percent error or whatever you want to call it, or percent markup in this case. You're just putting 150 minus 110 over 110. All right? And then multiplying by 100. So what do you get? You get 40 over 110 times 100. You could enter this into your calculator, but you could also pull some tricks first. All right? Pair of zeros simplifies to 4 11ths, which makes this 4 times 100, which is 400 divided by 11. All right, and in that instance, you get about 36% with that. Okay. All right, moving on. Go a little bit quicker now. Okay. This is translating set builder notation. Okay, a couple of things to remember. A set is something encapsulated in fancy braces, right? And in roster form, it's maybe the most easily understood because you can see the individual numbers. The way that you would read something like this, right, is that it is A is the set of X's, all right, and then there's this line here, right? Such that, is how you would read that in English. X is an element of the natural numbers. Of the natural numbers. And the second condition, X is between 2 and 8. Including 2, but not 8. Okay. I think that's the most intuitive way. Let me do it again. A is the name of the set. And then this is the description of what it is. A is a bunch of X's under two conditions. That is such that X is an element, the lunated epsilon symbol, it's stylized epsilon, means that X is the natural numbers, but in this boundary, basically, in this spectrum, all right? So the natural numbers, if you were to write them out, would be the natural intuitive counting numbers with your fingers. No zero, start at 1, right? Your fingers, you start with 1 thumb, right, or whatever. All right, so 1, 2, 3, jumping back on here, 3, 4, 5, 6, 7, 8, 9, and it would go on forever because natural numbers are infinite. Alright? But we have to meet the second condition. Alright, so the second condition and is that it's specifically in this spectrum, alright, from 2 to 8 essentially, but there's an equals adjacent to 2, which means that 2 is included. And notice that there is no equals adjacent to 8, which means 8 is not really included, it's just a reference boundary. Alright, so if we include 2, this is the natural numbers, but we're including 2, we're including this 2 here, this 3, this 4, this 5, this 6, this 7, and nothing after it, and nothing before it. Alright? That 2, 3, 4, 5, 6, 7 would be the answer. Alright, in roster form. Okay? Roster form is just listing it. Okay. Down here, determine the number of subsets and proper subsets. Right? Remember, and it might be a little counterintuitive, but every set is also a subset of itself. That's goofy, right? But it's true. Right? That's why they use these phrases, subsets and proper subsets. Right? It's not really important in this case, but subsets and then proper subsets, I'm going to put here and here. Proper subsets is doing what we would intuitively do, which is not include the original thing. Anyhow, if we're just asking the number of these, you don't have to describe every possibility. What you instead need is a formula. Subsets can be calculated from this formula. This is general, including the original thing. Proper subsets are everything except the original thing. Right? That's why they use the word proper. So it's 2n minus 1. N is the number of elements, that's the cardinal number. So it's 1, 2, 3. So in here, you're going to put, if I choose the word markup, 3, and then therefore there are 8 subsets in general, without having to describe them all. Proper subsets, you could reason, would be naturally 1 less than that, because it's excluding the original one. Right? But it would be 8 minus 1, which is 7. Okay. You could, if you wanted to, since it's not that, it's limited, it's only 3 elements here, you could sit there and calculate, describe each one, but you don't need to, you just need to describe how many there are. Okay. These are, describe these two. As equal or equivalent, right? Equal sets are exactly the same. They have the same elements. The only thing is that they can be jumbled, right? They can be jumbled up. They don't have to be in the same order technically, but they're basically exactly equal. The same cardinal number, that is the amount of elements, and the exact same elements themselves. Equivalent sets are only the same amount of elements, which is, remember, the cardinal number. All right. Let's see. All right, in this set A, you have 1, 2, 3. All right, so the cardinal number of A, you would abbreviate that as n, parentheses, and then A is 3, right? Because there's 1, 2, 3 things, right? The cardinal number of B is 1, 2, 3 things. But this is referring to countries, Brazil, England, and Japan, whereas this was referring to what appears to be the natural numbers, 1, 2, 3. So, of these two choices, what is it most closely? All right, they are equivalent. All right, they're not equal. Okay? And when you get to a Venn diagram like this, you have some operations here. Venn diagram to help answer. That's really the whole beauty of it. Okay. Given the Venn diagram of set A, encapsulated in red, and set B, encapsulated in blue, and then there's a sort of upside down horseshoe shape here, right? This is the intersection, which is synonymous with the word and what it is asking is for the overlap between the sets only. Okay. Now in the diagram, where is just the overlap of these two circles? The biscuit there that looks sort of like a Jesus fish, right? So the intersection of A and B would be B, D, and H. Because that's B, D, and H in the overlap. That's the thing they have in common. Right? When you have this one, this is a difference. Given the same Venn diagram, I'm going to erase this now, thankfully. All right, what is A minus B? The order in which this is written is important. All right, there's more or less a procedure for this. When you're doing a difference, as in this case, you're going to, one, cross out the matches first, and then two, circle the leftovers in the first, which in this case happens to be A. Right. So, if your A, I'm going to put this in red just to be consistent here, is F, E, G, B, D, H, and your blue is B, D, H, A, I, and you didn't have a Venn diagram, if you just had these things listed, all right, then you could follow this procedure. Cross out the things that match. Well, we already know it matches because we got the intersection from before. So there's a B here, and a B here, and a D here, and a D here, and an H here, and an H here. And we want the difference, so we want these things. So it would be F, E, G, right, for 25. Right. Another way of, if you have a Venn diagram, right, and you could basically just asking what is an A that excludes B, that would be this much of the picture, right? This cross-hashed area, which would be F, E, and G, F, E, and G. Okay? It's this minus anything that is involved in B. All right? Given the same Venn diagram, what is B apostrophe, which is known as B, the complement of B. The complement of B means everything not B. Now do beware, there are other things besides the contents of A and B here. There's Q, R, and S. So, in a situation like this, everything that is not B would be E, F, and G, and then Q, R, and S. E, F, G, Q, R, S. All right. These things, basically, all of that and all of this stuff outside of B would be the complement of B, B apostrophe. Okay. The next operation is cross multiplication, cross product here. Okay. There's a little procedure for this as well. Basically, if it's arranged as A in front, then you would do this. draw arrows from A to each B, because A is the thing in front. Right. Connect them basically, and then write as ordered pairs. And by that I mean something that looks like coordinates. Right? So these are the elements orange, banana, apple from A. So from A, I'm going to draw an arrow to each of the B's. And that would make this orange 1, comma 1. Orange, comma 2. And then I do it again. Banana 1, banana 2. This is a while back when we went over this the first time. It made me laugh to myself. You know, it was like, I can only imagine somebody's at home if they're watching this, and then maybe one of their family members comes in, and they go, "This is what you went to college for, so that you can learn the banana is 1." It's logic, I swear. You're like, no, banana is not 1. Banana is in tandem with 1. You know. Apple is connected to 1 and apple is connected to 2. So you have that as well. Apple, and then apple 2. All right. Now, technically, because these are set onto themselves, you would have these fancy braces on the outside here. But that's how you would have it, all right? Every element of A is tied to every element from B, right? All right. As a pair. Orange 1, not a pair, P-E-A-R, all right, P-A-I-R, all right, orange 1, orange 2, banana 1, banana 2, apple 1, apple 2. Kooky as that is, okay? Okay, now, I love this question, really, because to me, it really is kind of neat, right? I may be beating a dead horse here, but I think this is the best example to illustrate how to do something like this. There's a procedure to it. In order to answer any questions a lot of times about a 3-set Venn diagram, in this case, it's about music genres, so this is hip hop, right, encapsulated in red here, and this is rock. Called bedrock because of the B, and this is C as in country. All right. The procedure, I put and I'm leaving it here. All right. These regions in Roman numerals are places where you would put elements. All right, and it will always be in this arrangement: 1, 2, 3, 4, 5, 6, 7, and outside of it is 8. All right. When you are filling in a diagram, whatever problem it is, all right, do it in a specific order, right? In this order. All right, you do V first, all right, and then the things adjacent to it. So logically, so 5 and then 2, all right, and then 4 and then 6. Makes it easier when you do that. All right. Then go back and do 1, and then you do 3, and then you do 7, and then you do 8. It would be good to know Roman numerals, right? Just for this purpose of labeling. Okay. But this is the proper order. Always start with the dead center. Okay. So, based upon the descriptions you see here, of 500 people total, there's a contingent who are listening to hip hop, which would be 270. That would be everything encapsulated by red would be 270 total. But we have to take that number ultimately, 270, and chop it up into smaller regions. Okay? 320 would be rock listeners, which again, there might be some overlap, but the entirety of this blue encapsule here, the circle, would be 320. And similarly, the entirety of the green would be 160 for country. Then it tells you some cross-genre people. 140 listen to both hip-hop and rock, and 120 listen to both country and rock. 80 listen to both country and hip-hop, right? When you finally get down to it, the very last line, right? 50 listen to all three genres. What that is referring to is the dead center here, the Superman where the S would go right on his chest. All right, so you could start immediately by putting 50 there in that location, right? If this is where everything overlaps exactly, then there's a 50 inserted right in that space. All right, and from that little bit of information, we could now build the pedals here and then do outward the whole thing. All right. So how do we go through the next ones here? All right. Well, if we do 2, all right, we'll take advantage of some information here. 140, all right, listen, I'm going to go with this line here. Let me highlight it first. 140 listen to both hip-hop and rock, all right? This biscuit, which I'm just going to highlight, is what is referred to here. Hip-hop and rock is the Jesus fish, more or less, right? So what regions is that? It's 5 and it's 2, and we already know a portion of it. So in order to get to, it would be 140, the total, minus 50. All right? 140 is the total, that is hip-hop and rock, all right? And we know a portion of it 50, so we can get the missing information for 2. All right, what's 140 minus 50? 90. So we would have a 90 in here. Okay. Next, 120 listen to both rock and country. In this Venn diagram here, rock and country is this much. Pardon, yes. Alright, so I'm doing 6 in this case first. It's not going to hurt because of the way that it's written. Alright. If I stick with the order that I'm trying to encourage you here, I'll do this first. Alright. 80 listen to both country and hip-hop. So we'll come back to this. This would be country and hip-hop. Alright. It's 50, we know a portion of it, and we know the total. So this is 80 minus 50. What's 80 minus 50? 30, right? The green is a little faint, so I'm going to use black to fill it in. So this is 30. You would put a 30 here. Alright, now to get back to this, which is listed here. 120 listen to both rock and country. Again, that's this part here. This Jesus fish here. Alright, so if it's 120 minus 50, that would be equal to 70. So you have 70 here. Okay. Definitely, like I deviated a little bit because of the way that it was written in English. But you definitely want to construct these petals before you attempt these outer circles. It would be sparing you a lot of trouble. Alright, now when you get to region 1, region 1 is now going to take advantage of the original sentence here. Which, or at least this portion of it. 270 listen to hip hop. Right. So that's everything in here, right? All of this is 270. So if you want to calculate what is 270, pardon me, you want to calculate what is just 1 rather, you need the total, But then you're going to subtract the information that you have accumulated here of 2, 5, and 4. So we're going to make a sum first of 2, 5, and 4, which is 50 plus 90 plus 30. 50 plus 90 plus 30 is 170. 270 minus 170 is 100. So you'd have 100 here. Right? 100 plus 90 is 190, plus that is 240, plus another 30 is 270, the entirety of it. Okay? Makes sense, right? All right. Next portion of this is 320 rock people. That's again the blue capsule here. All right. So if we know the total, we can get this portion, which is just 3. This is the beauty of being able to write on this projection. So we need to know that this is 320 minus the sum, which I have to put in parentheses because we follow the order of operations that way, of 2, 5, and 6. So 90, 50, and 70. 90 and 50 is 140. 140 plus 70 is 210. 320 minus 210 is 110. So this is 110 here. And 2 more things. If we're getting now the last portion of green here, we need to take advantage of the total number, which is 160. And although it's very faint, I'm going to write this in black. All right, 160 minus 30, 50, and 70 combined first. That's 160 minus 150, which makes this equal to 10. Okay. Now, as far as the stuff that is outside all 3 categories here, all right, from that we would have to subtract quite a lot, right? The total is 500 people. So from 500, because I'm short on space, I would put it here otherwise. We're going to have to subtract the combined encapsulated circles here. 100 plus 90 plus 110 plus, shoot. Alright. There we go. Alright, 30 plus 50 plus 70 plus 10. Right. 100 and these together are 200 is 300. 330, 380, 450, 460. Together, this is 460. Right? 500 minus 460 is 40. Right? Which means that outside here, you might just put a 40. Okay. And now, based upon that information, right, you can answer some fun facts about this that follow. Right? The whole point of it is really the exercise of dissecting it, right, or constructing it rather. All right. Using the completed Venn diagram, right? How many people do not listen to country music? Right. Since you took the time to look at the Venn diagram, might as well go back and look at it here. And I'll scribble on top of this side of it. You could reason it through purely with the numbers involved here, but the Venn diagram would help, sort of validate a suspicion that you have. What is not country music? All the stuff in here would be not country music. Additionally, all of this would be not country music. And then there's all the stuff on the outside. So if we were to add all of that stuff up, right, that's maybe a more brute force way of doing it. Right? But you could add 40, 190, and 110. I'll put it here, right? 40 is outside, 100 is outside, 90 is outside, and 110 is outside. It's not that much stuff. So not country, which is the same as the complement of country. You could look at it, and there's more than one way to do it, but to me, if you're just going to add based upon what's in the picture, it would be 40 plus 100 plus 90 plus 110. These two together are 200. Plus another one is 300. This should be 340. An alternative way of doing this is using a formula known as the complement formula. The complement formula is this. The complement, which is again not C, is equal to the universal set, the cardinal number of the universal set, pardon me. The total minus what is C, right? The total is 500, right? If you instead decided to add these things that are C, this would be the sum of 10 plus 30 plus 50 plus 70. That would be 160. What is 500 minus 160 instead of adding a bunch of stuff? 340 one way or another. There's often more than one way to do something in math. The real purpose of a good math class is to exercise mental flexibility, to encourage that. Okay. So 340. Now let's fill in this table. This is an example of rules of divisibility. I would encourage you to memorize some of this stuff because a kid would be better off if they had it memorized. Right? Even if you yourself did not memorize it as a student, all right. Believe me, you learn a lot as a teacher, more than you ever will as a student, probably. Don't make the younger generation lack. Give them more. Not one thing in lieu of another. All right, one skill set in lieu of another. As many as possible. Cultivate an array of skills. All right. You could do some scratch work here, but you're just deciding whether you could divide. If something is divisible, it divides nicely, right, which essentially means no remainders when you divide. And you could tell based upon some rules here. All right. If something is even, then you could divide by 2 nicely. You get a whole number as an answer, no remainder. All right. This number, 963,888, ends in an 8. Therefore, it is even. All right. So therefore, you could divide by 2 very nicely. All right. It's divisible by 2. The sum of the digits is 9 plus 6 plus 3 plus 8 plus 8 plus 8. And you can keep doing this. You don't have to be satisfied with what you end up with. 9 plus 6 is 15. All right. 15 plus 3 is 18. 18 plus 8 all right, is 26. 26 plus 8 is 34. And 34 plus 8 is 42. Now, that may not seem like much progress, but because the number 42 is arguably beyond the realm of the familiar, but you could apply the same rule to this number 42. So what's 4 plus 2? 6. Can you divide the number 6 by 3 nicely that you get no remainder? Yeah, that number is warm, fuzzy, and familiar, so absolutely. So if the sum works, then the whole kit and caboodle works. So you can divide this number 963,888 by 3 if you need to. Right? I do this out of order because I usually think this way. All right, when you're simplifying fractions, this way this is applicable. If 2 and 3 both work, then 6 works. All right. 2 and 3 both work. So then you can do 6. All right. The rule for 9 is very similar to the rule for 3. All right. If we ended up with 42 from before, I'll use a different color just to make it contrast. If we got 42, all right, can you divide 42 by 9 nicely, or you're going to get a remainder? All right. This is why it would be helpful to know your multiplication tables, because you would recognize that 9 times something is close to 42, but not quite. Right? 9 times 5 is 45, and 9 times 4 is 36. So if you have 42 instead of those two things, it's not going to work. All right, so no. Right? It doesn't divide nicely by 9. You can divide almost anything by anything. The exception is you can't divide by 0. But, all right, in this case, it's not going to divide nicely. So you're not going to say it's not divisible. It's dividable, but it's not divisible by 9. All right. Does it end in a 0? Well, if you have 963,888, and I'm not changing anything, this number is 8, which is not 0. Right? So, nope, can't divide by 10 nicely. Right? Rule for 5. Does it end at a 0 or 5? Same problem. It is neither 0 nor 5. So I can't divide by 5 nicely either. Alright? The rule for 4 is that if the last 2 digits are divisible by 4, then the whole thing is divisible by 4. Now, if the last 2 digits here would be 88, can you divide 88 by 4 nicely? Yes, you'd get 22, right? So then indeed you could divide by 4. The rule for 8 is very similar to 4 as well. Last 3 digits. 888 divided by 8. Can you divide that by 8 nicely? No remainder? Yes, you can. Alright. Then there is, I've been told, a rule for 7, but to me it's more trouble than it's worth. So if you're just going to check 7, divide by 7, alright, and see if you get a remainder, right? It's a pain in the neck, alright, but you can do it. Alright, so here's 963,888 divided by 7. We'll see if we get a remainder. We'll use short division, alright, to get through it. 9 goes into 7 once with 2 left over. 9 goes into 26 3 times, which is 21. The difference is 5 left over. 9 goes into 53, 7 goes into 53 roughly 7 times, which is 49. The difference of 53 and 49 is 4. 7 goes into 48 6 times, which is 42. 48 minus 42 is 6. 7 goes into 68 9 times, which is 63. The difference of 68 and 63 is 5. 7 goes into 58 8 times, which is 56. So what you would end up with is a remainder of 2. Alright? This gives you a remainder of 2, so you say no. Alright? Could have used check marks instead of X's, but I felt that it is more emphasis this way. So, what is the number 963,888,000 divisible by? Alright, it's divisible by 2, 3, 6, 4, and 8 in that arrangement, or you can put them in order. Okay? So 2, 3, 4, 6, and 8. Alright, now these are very similar. Right. The real reason that a person learns divisibility, aside from it being a useful mental exercise, is to simplify fractions. It's one of the methods for simplifying fractions. Now, an alternative to that would be to look for a GCF. All right, and we're going to discuss prime factorizations. All right, the prime factorizations is either you could arrive at via fact tree, or you could try upside down division by prime numbers. All right. So, if you have the number, this will probably be the easiest thing. 220, you're going to try to factor it into primes. Remember, do memorize that the primes are 2, 3, 5, 7, 11, 13. You can't memorize all of them, but you can get a few of them to get going, all right? What is a prime number by definition? 2 factors, 1 and itself, all right? All right, 1 and itself, each. Those are its factors. Okay? 1 itself is the number 1 is not a prime number. It's neither prime nor composite. It's its own thing. It's its own thing. All right, anyhow, so what could you break up 22 into? You could try rules of divisibility because it's even. But to me, a shorter trick would be that, well, since this is ending at 0, it's 10 times something, right? What would it be? 22 times 10. Neither of these is prime, so you're going to break them down further. That would be 2 times 11, and this would be 2 times 5. The mark is done. So, what is the prime factorization of 220? Written nicely, it would be 2 squared times 5 to the first times 11 to the first. Okay? If you tried this other technique, upside down division by primes to arrive at the same thing, it's very literal, the way I've labeled it. So you would put 220 in a division box, which in the way that I was taught is an upside down orientation here. And you start with the lowest prime number that is divisible. So since it is even, start with lowest prime that is divisible. You would in fact use 2, right? 2 goes into itself 1 time, 0 times. That's not a prime number, and incidentally you stop when the quotient is prime. Since we're looking for a prime factorization, so you just continue with this. Keep using 2 until you can't anymore. That's become a dud. 2 goes into 11 roughly 5 times with 1 left over. 2 goes into 10 exactly 5 times. Alright? 55, not prime, so you're going to continue. It's no longer even. You can't use 2. The temptation might be to jump the gun and go straight to 5. And it would be 5. You already know what the reason is. Alright? But check 3 first. Alright? We've covered this. We have to eliminate 3 as a possibility. The sum of the digits would be 10, which does not divide nicely. So we now would go to 5. Alright? Only having considered that. 5 goes into 55 11 times. This junk on the outside is the prime factorization. Okay? Now, find the greatest common factor and the least common multiple of 25 and 35. I'll put them on opposite sides here. GCFs would be here. LCMs would be here. All right. We'll use factor trees. All right. Here's 25. Here's 35. The prime factors of this would be 5 times 5, which is 5 squared. The factors of this would be 7 times 5, which would be 7 to the first times 5 to the first. Save that. I'm going to write the exact same information here. If you're using prime factorizations to get the answer here, which is a useful technique for these purposes, you use them slightly differently, so you got to be a little careful. For GCF, all right, you're going to select, ironically, the lowest available power of factors in common. All right, now, of the factors that are in common is just 5s. So you're not going to include 7 at all. And of the 2, which is the lower power, 5 squared or 5 to the first? Just 5 to the first, therefore the GCF is 5. That means that if this was a fraction of 25 over 35, you would divide by 5. All right, and you'd get to the simplified answer, lickety split. Okay? Using the same information, but for a least common multiple, which is to do the opposite usually. Instead of simplifying a fraction, a lot of times you're doing the opposite. You're upgrading to a common denominator. You're going to select, I'll get out of the way in a second, I swear. Select, somewhat ironically, the highest available power of each unique factor. That means you don't really care if they match or not. You want to cover all bases. You want everything that is possible. Of the things that are in common, the 5s, which is the highest one? That one, so you're going to go with that instead of that. All right. I know that it's ironic because we're talking about least, right? And then we end up looking for highest, but that's just the way it is. Now, of the things that are not the same, that are not a match, we still need to include them because we need the highest available power of each unique factor, no matter what. So we're going to use this 7 as well. Now we're going to multiply them actually. 5 squared is 25. 7 to the first is just 7. So the LCM, the least common multiple of 25 and 35, is actually 175. Okay? Alright. Now we have some integer rules here. Oh, that looks like a mess. I put these here as sort of a reference. This is how I consider things. All right. In the case of addition, and it works consistently. In the case of addition and subtraction, it is the combination of the signs that determines the operation. Right. Meaning, what you see is not necessarily what you get; it's the combos that decide it. And the sign of the answer is always the same as that of the larger magnitude. Right. If you're given a double negative between the numbers, change it to a positive first. In general, if you end up with just 2 signs to compare, same signs you actually add, and if you have one of each, you actually subtract. Now you would apply that, I'm sorry for the lack of space, to this problem here. All right. If what you see is -4 minus -3, essentially, right? There's a double negative between the numbers. So what you would have to do is address this as a positive instead, which means that what it really is -4 plus 3. Right? Do you have the same signs? In which case you would add, or do you have one of each? In this case, you would actually subtract. This is a one of each problem, ultimately, with the correction that needed to be made. So that means that you're going to actually subtract, and that arrives at the digit of 1. As for the sign of the answer, it's always the same as that of the larger magnitude. 4 has a larger magnitude. It's further from 0 than 3 is. So since 4 was negative, the answer is negative. Okay. Then there's a different set of rules, similar looking, when you get to multiplication and division. All right. Again, I'm sorry for the lack of space here. You have to be aware they're different depending upon what operations you're starting with. If you know that you're either multiplying or dividing instead, the combination of the signs does not determine the operation. If you multiply, you multiply. If you divide, usually divide. The only exception would be if you had a fraction, perhaps. You know? Instead, the sign of the answer is decided by the combination. If you have the same signs, you get a positive answer. If you have one of each, then you have a negative. So this pertains to this here. All right. If you have same signs as you do in this case, that means that you're going to get a positive answer. All right. It's not telling you to do some other operation. Notice that there's a parentheses here. All right. This is not the same thing as the problem that purposely chose these numbers to show you the lack of symmetry here. This is a multiplication problem. This is an addition/subtraction problem. Just that one little distinction, double negative here versus nothing. But there's a parentheses included. So this is 12. Okay. So be careful. All right. You can verify with the calculator certainly, but you need to be strong in the foundational information. All right. Now, when you're converting from a mixed number to an improper fraction, remember there are 2 different styles of the same quantity. Right? Sometimes in algebra, the tendency is to use improper fractions. It makes working a little bit easier. In real life, when you talk to people, you talk to them mostly in mixed numbers. Like, for example, if you went into a store, Home Depot, and said, I want, 7/5 of a nail, all right, they might be confused by that. But if you told them, I want, 1 and then a little extra, the mixed number equivalent of, 7/5. 7/5 is 1 2/5, This is an awkward way of speaking. I want 7/5 of something, right? It's practical in algebra, it's good for that purpose, but in real life you would talk like this. I want 1 and a little extra, 1 2/5, Real life. The process of converting from a mixed number to an improper fraction works like this. I always draw it out. Right? You multiply these two things, and then you add them to the top. Right? 2 times 5 is 10. 10 plus 3 is 13. That's the new top. All right? And then you keep the same denominator, 13 over 5. 13/5 is awkward, but it is correct. Okay. If you were going to go the other way, I know you're not asked to in this case, you're dividing the top by the bottom. All right? How many 5s can you squeeze into 13? 2, which is 10, and the difference is 3. And then that remainder is your numerator, and what you divide by is your denominator, 2 3/5. Using algebra, convert the repeating decimal to a fraction. This is an interesting technique. All right? When you have a repeating decimal, that is, that there's an actual pattern, not like pi, which is 3.14159, whatever it is. You have the mark of the devil here. 666. The trick is to try to preserve a portion of the pattern. Right. That's one part of it. And then the way that you erase infinity is via subtraction. Right. And you have to remember some foundational information too. Move a decimal once, multiply by 10. Right. Move a decimal twice, multiply by 100, and so forth. If you want to move it 3 times, thrice times 1,000. Now here you have something that is just a single digit repeating. All right. The algebra of this is to involve the variables. So you say, like, this is a weird number, so I'm going to call this n. All right. N equals 0.66 repeating. All right. Keep in mind, I want to try to preserve some portion of this. I'm going to erase infinity via subtraction, but I want to preserve some portion of this. So I only need to scoot this over 1 space. If I multiply this 0.666 times 10, the effect is that it's going to just scoot this decimal point over ever so slightly. And that means that 10 times n, 10 times the number, is 6.666 repeating. All right? The reason for doing that, again, is I'm trying to preserve some portion of the pattern here. And since it's only 1 digit repeating, I just need to move 1 space. Okay. Now, I'm going to erase infinity by subtracting the original quantity, 1 minus n, 1n, from the incarnation of it that I have created, 10n. And that would be this. Now the beauty of it is that if I lock up, again, this would be great if it was on graph paper. Align the decimal places, as I should for adding or subtracting decimals. You can see what's going to happen. I have infinity stretching of 6's forever in both cases. But if I subtract the newfangled form of this, 6.666 repeating, minus the original form, 0.666 repeating, and they're all lined up, without having to analyze every little place value, these would cancel all the way into infinity and beyond, right? And that would leave just what is up in the front here. What's 6 minus 0? It's just 6, right? On this side of equals. And on the opposite side of equals, I have like terms. I have 10 minus 1, which is 9 with an n attached to it. This expression, 9n is equal to 6, is something that algebraically I can now solve for n, right, by rearranging the parts, right? It's understood that a number pressed against a letter is multiplied, and I want to isolate the n, I would have to move 9 from here to here. Whenever you go over equals, you perform opposite operations. The opposite of multiplying by 9 is to divide by 9 here, and whatever you do to one side, you're obligated to do to the opposite side. These will strategically cancel to 1. That leaves you with just what you want, which is namely the value of n, the number, in the style of a fraction, which you could reduce. They're both divisible by 3 because that's the GCF. So in one shot, you get to the answer. 6 divided by 3 is 2, 3 divided by 9 divided by 3 is 3. 0.6 repeating in the style of a fraction is 2/3. Okay, it's 37. I typed this, and I really should have written it so that it looked more like a fraction, but we're going to follow the order of operations. Remember, please excuse my dear Aunt Sally, a Pembas, right? Please, or Gems is another one. Please excuse my dear Aunt Sally. I don't have an Aunt Sally, I have an Aunt Josephine, who's my favorite aunt, by the way. But this is the order. Remember, you do things first, second, third, fourth. All right. The mnemonic device that uses whole words rather than initials, as in the acronym Pembas, all right, implies parentheses, groups. All right, things that are raised to an exponent, multiplication and division, addition and subtraction. When you get to things that are on the same tier, you do whichever is left. It's on the left. Same thing. Whichever is on the left. Addition and subtraction are equally important. Alright, I know that addition shows up first in the mnemonic, but in general it could be the subtraction. Same thing with division, right? So when you have a problem like this, 13 over 15, I'm going to write it out over here, minus 14 over 45. And then you're following it by dividing by 7 over 9. You have a choice between subtracting and dividing. Which is higher order? Division is higher order, so we should really focus onto these two portions of the problem. All right? Narrow thy focus to just here. All right, because of division. Now, when you divide, the strategy is to keep, change, flip. All right, which means you keep 14 over 45 oriented as it was. Then you change this to multiplication, and you compensate by flipping this upside down. So this would end up being 9 over 7. Okay. Now, what would be strategic is to, rather than brute force top times top and bottom times bottom, which works, all right, make it easier on yourself. You can use a calculator, especially if you want to validate a suspicion you have, but try to look for relationships. This is, again, why it would be strategic for you to memorize multiplication tables, because you'll see patterns. You go like, I know that number. All right, anyhow, there's a relationship between these two things, right, above the line and below. It has to be that way, not adjacent. 7 divided by 7 is 1, that's the common factor, and this would be a 2 behind, right? Simultaneously, there's a relationship between 9 and 45, 1 below, 1 above, all right? They could be directly or across, diagonally. 9 divided by 9 is 1, and this would be 5, right? It is much easier to simplify, to multiply now. 2 times 1 is 2 on top left over, and 5 times 1 would be 5 left over. Okay, so now what you have is this. You have the original 13 over 15 minus, because that's what's left over, 2 over 5 instead. Remember, when you combine fractions, when you add or subtract, you have to have a common denominator. All right, so this is the point of the LCM, all right, from earlier. You're going to more or less upgrade to something that is a matching denominator. Just so happens that the least common multiple of 5 and 15 is 15 itself. So I can upgrade this 2/5 to so many 15ths, right? What is it times 5 that makes 15? 3. And if I did that to the bottom in theory, I would have to do the same thing to the top, which means that this would end up being 6 over 15, right? The result is that I'm going to subtract just the top 13 minus just the top 6 here, and I'm going to get 7 over the common denominator. That's one thing you have to be careful of. When you add or subtract fractions, you don't subtract the denominators, you just have to make sure that they match. You can simplify it as an afterthought, but that's, not in this case. So you have 7 over 15 as your answer. There's a lot to that problem, right? It involves order of operations, division of fractions, specifically is the process of keep, change, flip, and then writing an equivalent fraction, which is involving the least common multiple, otherwise known as the lowest common denominator. Okay? And if integers were thrown in here too, that'd be great, right? Yay! Alright. Alright, now we get into exponents here. There's a table from a while back, if you dig through the pages I have in Canvas, that summarizes this. All right. This is asking about the power rule. Okay. Use the power rule. The power rule says that when you have an exponent raised to an exponent, you multiply them. All right. So 4 times 5 essentially. And you can write that as an abbreviation, 2 to the 20th, right? Which would be easier than actually writing out what it equates to, because it's a huge number. It's like 1,048,576, right? Part of the reason that we utilize exponents, powers of 2 in this case, is because it's an abbreviation for a very large quantity. Right, so it's more practical to write it in exponential form rather than its expanded form of the actual figure, I should say. All right, standard form. Scientific notation takes that to the nth degree. That's the ultimate in abbreviations, right? So if you had something, this is a perfect example. The mass of an electron, if you were to actually write it out, is this. Decimal point is here, and then these many, many zeros, and then the actual value in kilograms, all right? If you're going to convert from what is referred to as standard form of a number to scientific notation, it's going to be some decimal times some power of 10, essentially. As a technicality, just beware, the first digit here has to be non-zero. Even if it has all of the other features, if this is not a zero, if this is a zero in the front, it has to be a non-zero. It's not technically scientific notation. It's just remarkably close. So the trick to this is we're going to move the decimal from here to just in between 9 and 1. So it's 9.11. And then we're going to account for the number of spaces from here to there, all right, and write that as the exponent. So in the United States, the way that we write decimals to the right here, that is places to the right of the decimal point, is we're supposed to leave a little gap. We don't put commas. All right, we do things in groups of 3. So that's 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, and then one extra one would be 31. Right? Now, if you're concerned about whether it's a negative sign attached to the 31 or a positive, I don't want to confuse you when it comes to switching things the other way, because then I would reserve a direction for a specific sign value, positive and negative. What I would say is this: if you have something that is smaller than 1, all right, use negative. If you have something larger than 1, which you'll see the average distance to the sun, then you use a positive. So this would be appropriately negative 31st power. 9.11 times 10 to the negative 31st kilograms. All right, is the mass of an electron very abbreviated? Right? It's more practical in that form, right? Converting from scientific notation now to standard form, all right? The average distance to the sun, all right? In this case, I would use a sign with a direction, all right? When you move, or when you have a positive exponent, all right, you move the decimal to the right. All right? When you have a negative exponent, then you move the decimal to the left. I don't like telling people a rule for direction when you're going the other way, when you're converting from a number to a scientific notation, because these conflict then. All right? So if you see a negative exponent, you move your decimal this way. If you have a positive exponent, as you do in this case, this is a positive 8. All right? You're going to move your decimal that way. Number of spaces, 8. So in this case, 1.5 times 10 to the 8th, write the decimal 1.5. All right, and then make 8 waves in the right direction. So 1, 2, 3, 4, 5, 6, 7, 8. And then fill in the waves with little zeros. Okay, this is standard form. In the United States, the way that we do this is we put a comma on the left side of decimal point for every 3. Right? We leave spaces when we have the right side of the decimal point. So this is 150 million kilometers. Decimal is there. All right, in the standard form. All right, the average distance from the Earth to the Sun, because it moves, right? The Earth. Okay. All right, now down here we have factoring radicals. When you have sort of coffee here. When you have a radical expression, this should be a little hot here. This is an example of an irrational number. It's irrational, which means that it is infinitely stretching. It's infinite decimal, no pattern. All right? So you can't convert this to a fraction. Can't be a fraction, no matter what you do. Rather than round something like this, the argument is that, well, you could simplify it. You preserve all of the infinity, but you'll use smaller figures to express that quantity. Right? And what we do is basically this: the product rule of radicals, which says that ideally you want the highest perfect square, or if it's a cube root, a perfect cube, times a leftover. Right? If you consider the factors of 20, in pairs, it would be 1 and 20, right? 2 and 10, and 4 and 5. These are factors. All right. If I'm going to try to simplify this according to the product rule with this strategy in mind, highest perfect square times a leftover separate, what numbers am I going to choose? All right. 1 is a perfect square, right? 1 times 1 is 1. And 4 is also a perfect square. 2 times 2 is 4. They have identical factors. All right. Which one is the higher one? 4. And that is in tandem with 5. So this is the leftover here, 5. All right. The leftover is usually a prime number or a composite like 6. That would be impractical to factor further. You wouldn't make much progress with it. Anyhow, the benefit of doing this, if you choose the highest perfect square, in this case is 4, and the leftover of 5, at least part of this will escape the radical. What is the square root of 4 by itself? It's 2. So the simplified version of this is the exact answer, is 2, the square root of 5. If you check with your calculator, 2 times the square root of 5, it's the equivalent decimal of the original square root of 20. The only benefit of it is that you're using smaller figures to express the same irrational, infinitely stretching decimal with no pattern. All right? So this is better. I know that we have calculators and we're used to things being in decimal form and rounding, but this is exact. Exact is better than a rounded number, essentially. Okay? Now, when you have something like this, you're trying to add or subtract radical expressions, they have to have, in this case, in order to do this, to add or subtract radicals, they must, the terms must have the same radicand. The radicand is a fancy way of saying the guts of the radical. Right. So in this case, you see it's 5 square root of 3, little hat here, and this is square root of 12. They don't match yet, right? They must have the same radicand and technically also the same index, which is the type of radical. Type, squares, square root. Alright, that's less of a concern at this level, but nonetheless. So what you're going to do is you're going to factor 12. Right? Again, with this strategy in mind, highest perfect square times whatever the leftover is. If you have to consider factors of 12, right, it would be 1 and 12 is a pair of factors, 2 and 6 is a pair of factors, and 3 and 4 is a pair of factors. Thankfully, finite amount of them, so there's not many to choose from. 1 is always going to be a perfect square, all right? But you want the highest one possible. So we're going to go with 4 again. So this is going to be the square root of 4 times the square root of 3, because that's what works in tandem to make 12. All right? Again, the benefit of doing this is that at least some portion of this will escape. So what you end up with is 5 square root of 3 minus 2 square root of 3. And now we meet the criteria that were required here. The terms, this is a term and that's a term, separated by a plus or minus is a term. All right, they have the same guts, radicands 03, and they're technically both square roots. So if you want to worry about the index, that's the number that would be here or here technically. In the case of square roots, they don't put the 2. All right, anyhow, what you're going to do is just simply subtract the outside. So it would be 5 minus 2. And that makes this 3 square root of 3. Okay. Moving on. Okay. Oh, the blue sticky dinner. Okay. This is from section 5.5. Identify the property as commutative, associative, or distributive. Right? What do commutative and associative tell you? basically that the arrangement of the parts doesn't matter, right? As long as you're just adding or as long as you're just multiplying, you can do them in any order that is convenient for you. Distributive property is, although it's something you could apply to arithmetic, it's more useful in the case of algebra, I feel. All right. This is an example of distributive property, because if you distributed the outside thing, that is, you multiply the outside by each of the inside contents, that's what you get. 2 times x abbreviated is 2x, and 2 times 3 abbreviated is 6. All right. So you could write something this way, or you could write it that way. The benefit is that you can get rid of the parentheses sometimes. Okay. Now, as a reminder to you about mathematical systems, I left this little blurb. A mathematical system is essentially a set, so you see things in fancy braces, and an operation is usually adding or multiplying. A group is a more specific example, all right, and it must meet 4 criteria. All right. Even more specifically, there are abelian groups, which means they have 5 criteria. All right. Here's an example to work you through. All right. Check the group criteria of the set for the natural numbers under multiplication. All right. The natural numbers are, we'll start with this, starting from 1, 1, 2, 3, 4, 5, 6, 7, and it goes on forever. So we indicate that it stretches forever by putting ellipses. All right. Now the criteria, and this is for multiplication, all right, are as follows. Number 1, is this set of natural numbers closed under the operation of multiplication? In other words, if you multiply, are you only going to produce more of the same type of thing? Are you only going to end up, as a result of multiplying natural numbers, more natural numbers? And the answer to that is yes. All right. 1 times 3 is 3. 2 times 8 is 16. That's a natural number, and so forth. All right. Number 2. Is there the appropriate identity element included in this? For multiplication, the identity element is 1. All right. For addition, it's 0. All right. In the case we're talking about multiplication, so is 1 essentially included in this? Yes, it is. So far, so good. All right. Now, what about the inverses? All right. Inverses, it would be good to know this formula. All right. An element times its inverse, the appropriate one, would equal the identity element. So in this particular example, if we took an element, whichever one it is, and multiplied by an inverse, would we get 1 as an outcome? All right. Is there anything times 1 in here that would, we have to do it for every example, is the truth of the matter. All right. Well, you have the number 1 would produce it times itself, so that means 1 is both an element and its own inverse. But what if you did the next one? What's 1 times 2? Would you get 1? You wouldn't, right? What you would actually need in this case, when you have multiplication, you would need reciprocals. That is to say, you need fractions. Right? Are there any fractions in this list? Right? Like, for example, if you had 2, if you multiply by a half, you would indeed get 1 in that case. Right? Because half of 2 is 1. There are no fractions in this. So it fails at this criterion. Okay? If you were talking about addition, just out of curiosity, the element plus the inverse would have to equal 0. So the inverses in the case of addition would have to be the negatives, basically. Opposite sign. So basically the negatives. All right. We're not concerned about that because we're not doing addition, but just beware. All right. Often they tell you that it's associative and that it's commutative in this case. But what happened was it didn't meet the 3rd criterion. All right. So therefore, immediately, it's not a group. All right. Not a group. All right. Because there are no inverses. Okay. So you won't even care about anything beyond that. All right. Now this is an example of how you would read a table. I'm going to minimize that just a little bit. What time is it? 20 hours, right? Okay. Here you have clock 12 arithmetic. All right. The set of clock 12 arithmetic would be starting at 1 and ending at 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, it's 13 elements. Don't drop stuff. No. Okay. Forgive me. And we're going to go through the same thing. Now, if you're given a table, as you are in this case, you could check things by, in some cases, pulling some tricks. All right. Is the set closed? All right. If it were closed, that means that you'd only have more of the same stuff in the set. Like in the case of the last example, you'd only have more natural numbers by multiplying. All right. In this case, you just have to look at the table, right? Do you see anything weird in this table? Anything that isn't an element from 1 to 12? Is there a number 13 here? Is there a number -9 here? No. So, since there isn't anything bizarre showing up in this table, I'm going to minimize just a little bit more. What you could say, since there is nothing weird here, that yes, it is closed. Not anything weird, it's closed. All right, onto the operation of addition in this case. All right, the identity elements. All right, an identity element again would be, if you're reading the table, it would be the column headings. These are the column headings. And the row headings somewhere in the table. All right, and they would intersect. They have to be exactly in the order that they're supposed to be. So what you see here is that here are the column headings, 1 to 12. Sorry, my mark is dying. Here are the column headings, and here are the row headings. They just happen to be all the way in the end here. All right? And where they overlap is the identity element. All right? So is there an appropriate identity element here? Yes, in this case, clock 12 arithmetic's identity element is the number 12 itself, all right? Are there inverses, all right? The best way to do this, there's a trick to this, but I would go with the formula, all right? The identity outnumber the element, all right, plus the inverse should equal 12, all right? Is there an inverse for every element? Yes. 1 plus 11 equals 12. 2 plus 10 equals 12, 3 plus 9 equals 12, and so forth. All right, there is a diagonal line that would basically be produced heading up in this direction if you check. All right, 1 and 11, 12, 12, 12, 12, 12, 12, 12, 12, 12, 12, 12, right? But I don't want to confuse it, even though that is something you can read from the table, with what follows. We're going to assume it's associative, and now we're going to check that trick for commutative. There's a line of symmetry about the main diagonal. What that means is this. If you have a table like this, and you draw from the top left down to the bottom right, an imaginary line that stretches from here to here, is there symmetry about the line as you go down it? Yes. All right. 1 and 1, 2 and 2, 3, 3 and 3, 3, 4, 4, 4 and 4, 4, 4. All right, 5, 5. You see symmetry as you go down this line here. So yes, it meets that criteria. All right. If we assume it's associative without having to check every combination. Is clock 12 arithmetic under addition in a Bellian group, meaning that it meets 5 criteria? Yes. Okay, here we have modulo systems. I'll zoom in a bit. Here's a little information to get you going. modulo n system, or mod n system, consists of a set and m elements, and a binary operation. All right. Let's see. Because these are finite systems, we have limited elements, and therefore they're cyclical in nature. Therefore, we would be required to express any larger quantities in terms of the established set of elements only. This is known as congruence, and they use this sort of special equal sign, explaining what equals what in the specified system. Right. So as an example of that, if you look at a mod 8 system, a mod 8 system goes from 0 to 7, but there's 8 digits total here. All right. You always start, when you have modulo systems, always start at 0. All right, for mod systems. Right. And if we divide by any number, by the modulus, the remainder tells us what that number is congruent to. So for example, if we took 60 and divided by 8, we'll see what it translates to, right? 8 goes into 56 roughly 7 times, which is, 8 goes into 67 times, which is 56, and the difference is 4. So that means that the remainder is 4, all right? Therefore, 60 is congruent to 4 in mod 8. Okay? Moving on. We're going to check the theoretical probability of two things: rolling an even on a one thing, of rolling an even on a 6-sided die. All right. The theoretical probability of rolling an even would be equal to the number of outcomes favorable to the event of rolling an even over the number of elements in the set. Okay? So if you have a 6-sided die, you have 1, 2, 3, 4, 5, and 6 to choose from. How many are there in this set entirely? 6. All right. How many things are even? 1, 2, 3. What is this simplified? It's a half. So 50% probability. If you're going to calculate the odds in favor of something, this is a different formula. Remember, odds and probability are not exactly the same thing. One could be derived from the other. There's formulas for that. But odds in favor are written like this. It's equal to A over B, very simple fraction. All right. The bottom is not a total, though. All right. The top is favorable outcomes. All right, and the bottom is unfavorable. So this versus that. All right. If you're looking for odds in favor, it's favorable on top. If it was odds against, it would be this upside down exactly. Drawing a queen at random from a standard deck of 52 cards. How many queens are there in 52 cards? There's 4 of them, right? How many are essentially not queens, right? 48. So instead of putting a 52, because that would be a total, we're using the things that are not that, the complement essentially. All right, if you reduce this, it's 1/12. Bring the end here. All right, expected value, this is a formula. Expected value is this formula. It's a sum of probabilities and the benefits, or the what's the opposite of a benefit? I'm struggling to think of the word. Deficits? I don't know. Think of it some other time. It's the sum of benefits, basically, and things that are not beneficial. Right. So you could use as many of these terms as necessary. In the formula, you see subscripts of n, as in the nth example. On a multiple choice test, there are 4 possible outcomes to choose from for a question. All right. The way that it's divvied up is that if you get 2 points for anything that's correct, you get a half a point for anything that is incorrect, and you get no points for things that are neither. All right, left blank. I thought about this from the last time that I went over it, and I'm like, I suppose that you could maybe address the probability in a different way than I had for this thing, but the last term, if you include it, is going to be 0 anyway. Anyhow, let's calculate this first probability, the probability of correct. All right, that would be the number that are correct out of 4. It would be 1 out of 4. What's the award for that? 2 points. Let's calculate the probability of incorrect. All right, that would be 3 out of 4. All right. That's the majority, right, of a multiple choice question. So you would definitely have those 2 things at minimum. Now, when you get to the other thing, it's debatable, I suppose, but it says no points will be awarded if the answer is left blank. I thought about this, and I'm like, well, you could instead of phrasing it as neither, maybe calculating a probability of blank, out of 2 options. All right. If you think about the set as being blank or not blank, right, that's basically 2 options, right? It's binary in that respect, all right? So of the 2, one could in theory say that what's the probability that something is blank? All right, it's 1 out of 2. It's either blank or not blank. But the award or the loss is basically 0 anyway. It's no points. So it really doesn't matter. It's going to be something times 0, right? Which means that this third term, if you include it at all, is going to be destroyed, right? Excluded, right? I did forget to add that this is a half a point here. All right. So, and it's minus, you're subtracting a point from the context of the problem. This blank, officially a dud. Okay. So, what is 2 times a quarter? Top times top, bottom times bottom is 2/4. It's positive. You can simplify it to whatever you like. What's 3 times negative, 3/4 times negative 1/2? This would be minus 3/8. Right? So you have 2/4 minus 3/8. You would have to, in theory, upgrade 2/4 into so many eighths, which would be 4/8. But overall, the expected value would be a positive, so it would be a benefit in the long run because it is a positive. But it would be 1/8, all right, of a point. All right. This third term, whether you choose to include it or not, all right, is going to be times 0. All right, so it's really irrelevant anyhow. All right. The expected value is positive 1/8 of a point. Would it be to your advantage or a disadvantage? It would be an advantage in the long run. All right. All right, because it's positive. Yeah. The expected value of a lottery ticket is $1, and the cost is equal to $8 positive. Determine what the fair price of for the lottery ticket would be, all right, if the dollar value is the result of the expected value being 0. All right. There's a formula for this. Fair price is the expected value plus the cost. So if the expected value you're told is negative $1, it's minus 1, and the cost is plus 8, the fair price would actually be plus $7. Right. What that means is that if this was factored into the original probability calculation, all right, the end result would be 0. You would be neither a gain nor a loss. It would be neither a benefit nor a disadvantage. All right, so you'd be breaking even if this is the actual fair price, all right, instead. Now we have calculate the total possible outcomes. The counting principle can basically tell you that. M times N. That's total possible outcomes. All right. For 2 activities consecutive, tossing a coin, which is two possible outcomes. There would be 2 here. And rolling a 6-sided die, which has 6 outcomes. Right? So in tandem, you would have 12, right? Total, right? You could do it via that calculation, or if you did it via a tree, it would be heads and tails, and then a 1, a 2, a 3, a 4, a 5, a 6. And then for tails, 1, a 2, a 3, a 4, a 5, a 6. And you would have 12 total again. Sorry, I'm rushing a little bit. Let's see. Last 2. Let's see, we're almost 3 hours here. Calculate the probability of drawing a queen, drawing a heart or a face card from a standard deck of 52. When you have a problem like this, you have to decide whether they are mutually exclusive or not, right? Not. Mutually exclusive means can't be simultaneous. Right? Can be simultaneous. Alright. Can you draw a card that is simultaneously a heart and a face? You can. So this is not mutually exclusive. And therefore the formula that you would use is this. The probability of a heart or a face is equal to the probability of a heart by itself plus the probability of a face by itself minus the probability of those things simultaneously. All right. That's a derivative using hearts and faces in place of A's and B's in the formula. Okay. How many hearts are there in a deck of 52? All right. There would be 13 out of 52. How many faces are there? You know, the portrait cards. There's 3 from each suit, and there's 4 suits, so there's 12. How many cards are both a heart and a face? The Jack of Hearts, the Queen of Hearts, and the King of Hearts. So that's subtracting out the 3 examples so that you don't count something more than one time. Right? That's why there's a minus in this version of the addition formulas. All right. So it's 13 plus 12 minus 3 out of 52. 13 plus 12 is 25. 25 minus 3 is 22 out of 52. If you simplify by dividing each of these by 2, you get 11 out of 26. So just shy of 50%, right? 13 out of 26 would be exactly 50%. All right, last question. Calculate the probability of getting an A at random given that you get a grade of higher than a D. This is a conditional probability, so notice the phrase given that, right? This would be the probability, if you wrote it out, of getting an A given that is this line, a grade greater than D. And it would be translated into the formula, the number of outcomes favorable to this intersection. A grade greater than D, and I'm using the intersection symbol in tandem with the word and because I like it, A over the number of things that are grades greater than D. Right. Start with the bottom. Of these choices A, B, C, D, E, A, B, C, D, F, how many are things greater than D? That's the denominator, it's 3. Right? the intersection of those three things and the one example that is an A is how many? Just one. Okay. Alright, so you have a 33 1/3% chance, so 1/3. Okay? And that, folks, is it. Okay? Well, thank you for a lovely semester, even remotely, and for listening and tolerating my ranting. Anyhow, your grades will probably be posted tomorrow afternoon online, okay? Take care out there. Be careful.